What's up guys, welcome back to the next video learning awesome and discrete mathematics. My name is QTS Dani and you guys watching my channel Croywood. So in this video we're gonna see the predicates and quantifiers. A sentence that contains variables is called predicate. We look at the following statements: x is greater than 5, x is equal to y plus 5, x plus y is equal to z. The truth values of this statement has no meaning without specifying the values of x, y, z. However, we can make the proposition of such statements. So, x is greater than 5. So, if you look in here, the x is subject and is greater than 5 is a predicate. If you look in here, so we gonna go again here on top. A sentence that contains variables called predicate. So any of them, all of them has a variable. If you look in here, it's called predicate. And the truth values of these statements has no meaning without specifying the values of x, y, z. So if you don't specify the x, y, z of this above here, so it means it's got no value. So we can make a proposition of such statements. So this is a proposition: x is greater than 5. So this guy is x, and is greater than 5 is a predicate. We look in here, and we look in here, and same goes with the rest. So the simplest example we can give you is that x is greater than 5, and look at the x, and the x is subject, and is greater than 5 is a predicate. So a predicate is a property that is affirmed or denied about the subject. So either we can affirm or we can deny about the subjects. So we have a unitary predicate, we have a binary predicate, and we have a ternary predicate, and ray predicate. So the unitary predicate, we put it at say as a, and you put it as x, and that's unary because it's only one. So the put a b, and the b is going to be x, y, x, and it's going to be y, and that's going to be the binary predicate because the y is binary because it's 2. Sorry, my writing is not good, but as long as you guys understand. And the sum of this x, y, z, and we put a c, which is going to be the sum, and the sum is going to be x, y, z. So we have x, y, and we put a z. And this guy is called ternary predicate. So we put a ternary. Okay, so we have a of x is a binary, b of x, y is we have a of x is unary, we have b of x, y is a binary predicate, and we have a c, x, y, z is a ternary predicate. And the last one is we can put a p of x, y, z and t. So we put x, y, z, and t at the end. And what's this one? This one's going to be n array predicate. So we put an n, so that's how we're going to write this. So the first one's going to be the a of x is a unary because only one. That's what we call unary. The binary, if it's 2, we call it binary. So binary is 0 and 1, and unary is could be either 0, it could be either 0 or it could be 1, but it can't be both. So this binary is, you can write 2, but it's not a 3 or 4. As ternary, you can put a 4 in computer science is 0, 1, 0, for example, and that's going to be ternary because 3. And when it's more than 3 and is p, x, y, z and t, then you call it n array predicate. That's what we call it, n array predicate. Alright, so I'll remove this. So keep in mind, there is a unitary predicate, there is a binary predicate, there is a ternary predicate, and an array predicate. All right. A predicate becomes a proposition when we assign it fixed values. However, another way to make a predicate into a proposition is to quantify it. That is, the predicate is true or false for all possible values in the universe of discourse, or for some values in the universe of discourse. Such quantification can be done with two quantifiers. There can be many types of quantifiers in English, but in mathematics we stick to the two. So the first one is going to be existential quantifiers, and the second one is going to be universal quantifiers. So now we're going to see the existential quantifiers and the universal quantifiers in the next slide. So there is a little bit here, I'll remove that. A universal and existential quantifiers. The existential quantifiers is, and we put it the other side, E. So this, if you look in if it looks like E, so the E is like that. But if you remember, there exist or there is, if you guys see like this, something like this, it means is there exist, or like this, it means there exist or there is. So that's existential quantifiers. Is we put it the other side of the E like that, and it's read that there exists or there is. Okay, and its example, and the example is there exists, there is a number less than 0. So we have there exists x, and there exists, that's how we're going to read it. There is x, and this x is here, which is less than 0. So we're looking here, there exists, there is a number less than 0. That's how we're going to read this. So if you see here the other side of the E, so that's not the normal E is like that. But if you see like that, and you put an x, and what is your x? X is say if it's greater than 0, then we say there is a number which is greater than 0, but in this case there is a number which is less than 0. Okay, the universal quantifier. So we've seen the existential quantifier, and that's existential quantifier, it says there is or there exists. And now we're going to see the universal quantifier is going to be upside down A, and is read for all, for every. So the universal quantifiers is this guy here, and it reads that's for all, or sometime you're going to see that's for every. So when you see this one, this means for all, and when we see this one is means there exist. That's the other side, E. And the example is if when you see upside down A, it means for all and for every x, and it says for all every number is greater than or equal to 0. So even you see here it says for all x, it means for all x, and for every number is greater than or equal to 0. So that's how we're going to read this. So now we have statements, and our statement is for every x there is some y such that y is less than x. So that's how we're going to read for every x. That's what the first one, for every x there is some y, and there is some y such that y is less than x. That's how we're going to read this one. So when we see like that, and as I put it there, for every x there is y, and there is y. Why there is a y? Because we put it here, there exists. Sometimes when you see this, there exists, and sometimes it says there is. So now we're going to read it as there is. For every x there is some y such that y, not normally, you don't get confused, because such that you guys going to see like that too. So even there is a pipe, and it means such that. So if you gotta say x such that say y is greater than or less than x, for example, if you see like that. But sometimes when you see like that, the pipe, it means that such that. But we're looking here for every x there is some y such that y is less than x. So that's how we're gonna read it now. So is this true? The answer is depends. Before we begin, we see natural numbers, and before we begin to the next slide, we're gonna see the natural numbers and whole numbers. So what is the natural number and what is a whole number? The set of numbers 1, 2, 3, 4, 5 is called counting numbers or natural numbers. So the first one, if you see that if you can count it by your fingers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's called counting numbers because you can count it with your finger, or natural numbers because that's naturally. That's natural, that means you have a hand, you have a foot, and that's natural around you. You can count it, and you don't have to include 0 because that's, if you include 0, this is not going to be natural number. The set of numbers 0, 1, 2, 3, 4, 5 and so on, we call it whole numbers. So when you see the numbers without 0 because your fingers doesn't have a 0, it's called counting numbers or natural numbers. If you that doesn't have a 0, it's a counting numbers or natural numbers. And if you see the 0, we call it whole numbers because it's including 0. And you can use it for mathematics, this one we can use it computer science, and you guys are going to see that's whatever we do indexing, whatever we do in computer science, our calculator, for example, is a whole number. It's not a natural number because the natural number is for us to count. So sometimes you guys don't, because with the natural number normally you guys don't say the -1 house or -2 house. You guys don't say that the -1 road. So you always say 1 road or 2 road, 1 country, 2 country, 1 person, 2 person, or you can put whatever objects you want to use. So you can put 1 tree, 2 trees, 3 trees. You guys don't see the 0 trees, or you guys don't see -1 or something, because that's going to be integer. Okay, so the set of numbers 0, and keep in mind the whole numbers is 1, 2, 3, 4, 5, and keep in mind the counting numbers is just natural numbers 1, 2, 3, 4, 5, and the whole numbers is when you guys include 0 with the natural number, it's going to be the whole numbers. So in mathematics we almost always quantify over the natural numbers. So we're going to go for a walkthrough again. We've seen the existential quantifiers is looks like E, but the other way around, and it reads that there exists and there is. For example, if you see there exists, there is a number which is less than 0. The universal quantifier is upside down A, and we see is for all, for every. For example, is going to see that for all x, every number is greater than or equal to 0. That's how we're going to read this. So we have these statements, and we're going to see that's for all x, there exists some y such that y is less than x. That's how we're going to read this. And before we continue to the next slide, and in the next video we're going to see more, but before that we're going to see that the set of what is natural number is the whole number. Natural numbers and is that the one you count with your fingers is 0, and if you add 0 to the natural number, it becomes a whole number. Alright guys, that's it for this video. If you have any question or comment, leave in the comment box. Otherwise, I'll see you guys in the next video, and bye.